Dear Junior, dear Professor, and dear sponsors and participants for the MIT Battery Consortium Phase 4, it is my great pleasure to present you the modeling of fragmentation of pouch cells in hoop direction under axisymmetric indentation. My name is Junho Lian, and I'm currently assistant professor at Aalto University in Finland. Following the presentation given by Dr. Wei Li, I assume you have seen that at the consortium, the MIT team has already built up a very universal and intensive modeling approach to describe the large deformation and failure behavior of lithium-ion battery, not only under quasi-static, but also dynamic, anisotropic, and even different SOC conditions. It shows very good predictive capability, for example, under plate strain condition when we're loading under a cylindrical rod, and it shows good prediction for the shear fracture, as well as the good prediction on the force and displacement curve. But the overall approach is also suffering from one drawback, that is when we just switch from, for example, the plate strain condition to axisymmetric condition, we had to use a different set of parameters to capture the right moment of fracture. So if we just simply using the same one, you can see we will get a very premature fracture point. And my presentation here is exactly zooming in to this problem and gave you some fine solution to overcome this issue and even gave more features, especially with respect to the hoop cracks. Before we go to reconfigure our constitutive equations, we would like to first take a look at the failure mechanisms of these two cases. So first of all, we have this plane strain condition. We have a very clear and clean shear fracture. And this is not only for plane strain. If we look at the test with a very large flat punch, which is also an axisymmetric condition, you also see this very clean and clear shear fracture. And not only for indentation test, these are the two figures for the pinching. You can clearly also see, as I indicated here, there are also two very clean and clear shear fracture. That's why we're concluding the first failure mechanism for the battery is exactly so-called shear failure dominated fracture mechanism. And for the second, when we just look at our axisymmetric condition with a hemispherical punch, this is the one with a rather small radius. And you can see here we don't see, first of all, that shear fracture, but we rather see a lot of micro cracks that you don't see at the moment very clearly, but I will show you with the clear figures later. And here you can see they're just very much degraded material region with several micro cracks. And when we just change a different punch ready, you can also see this kind of degraded region still there, but we clearly see the shear cracks with even multiple lines, either through thickness or not. That's why we're concluding for the second failure mechanism is we're gonna have damage. So they're referring to all these degraded micro cracks. And in addition to that, we also have this kind of shear failure possible. That's why we're referring to the second mechanism as the damage and shear failure concurrent mechanism. And this is the model that we developed before, and you have the classic dashbed flag model on the left-hand side, and we introduced the crack initiation, which is either Cock-Verlethy or Johnson-Cook. But the feature is once this kind of a criterion is reached, exactly, you're leading to the final fracture. So once it is reached, the material is completely deleted, and we will lose the load carrying capability. And you can see this is not reflecting the damage that we have been seeing from previous slide. That's why we made a modification to the model to introduce a term called damage evolution. The damage is formulated with respect to the maximum principal strain, as you can see here. So in this case, the damage initiation criterion is what we have seen for those two criterion. And when these are met, the element will not be deleted. Instead, they will go to a stage to accumulate damage. Only when the damage is reaching a critical value, and this will be a parameter for us to calibrate again, and this will lead to the final fracture of the battery. This is the result that we just applied our new model to the plane strain condition again. As you can see here, the red one was our previous test results or simulation result, and the green one is the new result. You can see the difference is rather small, almost negligible. And if you just look at the failure pattern, you can see we still capture a very clear shear failure for the plane strain condition. If we just move to the axisymmetric condition, and you can see here, instead of the very premature failure point, we significantly improve the load carrying capability and improve the prediction of the fracture point. If we just look at how the fracture pattern looks like, and this is it. Now let's just make a comparison between these two types of fracture. Here I'm showing you the contour of damage. So the red here basically is meaning we have the damage as the critical value, which is also referring to the elements that have been deleted. So for the plane strain condition, you can see the critical damage values are only restricted to a very narrow line, which is the clean shear fracture. But for the axisymmetric condition, you can see we are having exactly the damage accumulated right under the punch, and we also have a development of this kind of a shear failure in the end. So here I'm going to show you in a rather progressive way to just see how they developed. Let's see, first of all, we're showing you the first point. Here, this is the damage, critical damage or the crack initiation. So the crack is triggered rather in the kind of center of the sample through the thickness. And then soon after that, you will see the crack is propagating almost through the whole thickness and very quickly to the final failure point when the whole through thickness crack is formulated. If we look at the axisymmetric condition, let's focus first of all the point when we have the premature fracture. And here I'm showing you two contours. The first one is the so-called damage initiation. So this is indicating if the material has reached the damage initiation criterion, so the Cockcroft-Lattin criterion in our case here. And here you can see some elements right under the punch have reached the damage initiation. If we are using our old model, all those elements will be exactly deleted, and that is the reason for the drop of the load. Now they're not deleted, they're entering the damage accumulation phase and they start to accumulate damage. So the value is rather small. This is the second contour. So when it's red, meaning there will be final deleted. And now if we move to one point just ahead, you can see more and more elements have reached the Cockcroft-Lattin criterion and they're entering the damage initiation, but their accumulation is not so much. So their damage evolution is rather slow and it's rather progressive. And until we reach the final point, and a lot more elements have reached the damage initiation, and you can probably see these two lines, and they are finally leading to the final fracture, and there are these clear shear fracture lines. So they are the cause for the final fracture, actually not all this damage right below the punch. With that, I've showed you how we reconfigured our constitutive equations and how we managed to use one set of parameters to predict the failure behavior under both plane strain and axisymmetric loading. You're probably still wondering, for this especially axisymmetric condition, what exactly is this damage especially when we're just saying here. And the second is when we just switch from the small punch to a large punch, how could we see or why at a certain point we get this shear failure again? Can we get them predicted as well? So first of all, to just answer the question about damage, we made a X-ray computer tomography analysis, as you can see, to just watch from top and on a specific plane here. And we got such a image here. You can clearly see this damage actually are referring to many small cracks. You can see also at the center there is a degradated zone, but afterwards you really see all these small fragmentations in hoop directions, and we just simply call them hoop cracks. And we didn't manage for our sample to do a XCT image for the large sample, but you will see the colleagues from the Oak Ridge National Lab have exactly done a similar study, and they of course are using different types of batteries and also with different SOC condition and different kind of punch radius, but they exactly discovered a similar observation as I just showed you. So this is what they have done with the XCT measurement, and this is also a 2D. You can already see this kind of hoop cracks developing along on the different directions. What they have made is they managed to get a side cut as well. So the side cut is from here, and you look from, for example, left, and you can see here we just right under the punch we see a lot of small cracks, and not only to the metal collectors and also to the granular materials, but under the punch a little bit you can also see all these small cracks existing in both metal and granular materials. And you can also see from another angle when we just cut it horizontally, and you now see better all this kind of damage of our materials. And if we just look at in a 3D view, you can clearly see here we have a rather kind of degraded zone of the material, and after that zone the crack is just developing in relative direction. So these are the so-called hoop cracks. And they also made this kind of measurement not only for one radius but also for several different punch radius. And we have just looked at the small one with 5 millimeter. If we just move to the largest one, which is 12 here, and skip in between, you can see here for the largest one clearly, instead of just the damage, so for all the ones smaller than 12 millimeter, you don't see really a through thickness shear failure. You only see all this damage. And here is a point you really see at least one clear through thickness failure developing, and also several maybe not through thickness but also shear fracture. And if you just look at from the top view, you can see there are not so many hoop cracks anymore. Actually, this kind of shear fracture, they're just developing either horizontally to the width direction or to the length direction of the battery, and they're just going through the whole battery, either just as a straight line or in the zigzag direction. So this observation is exactly corresponding to our observation with the large EV batteries. And we would like to see if our model gets that predicted as well. So we try to use exactly the same model with the same set of material parameters, but to review all these features, we had to build up a 3D model instead of 2D. So this is the one first with a small punch. You can see we really capture quite well, not exactly, but quite well, the degraded damage zone in the center and also this hoop cracks. This is very similar if you just recall the 3D case, and this is the 2D case, not exactly reflecting what we see from the simulation here. But this is a very good reflection of the hoop cracks already for the small radius, and we didn't see actually a through thickness shear fracture for this small punch. And when we just switch it to the large one, you can see here, automatically, we already see all this kind of through thickness shear fracture. And of course, you also see a little bit damage or degraded zone right below the punch, but they're not the dominant feature anymore. And we just capture this transition from this kind of hoop cracks dominated case to the shear fracture dominant case again. And with that, I would like to conclude my talk. First of all, I just gave you two main failure mechanisms that exist in the lithium-ion batteries. The first one is a shear failure dominant case, and the second one is damage and the shear failure concurrent case. And we proposed a unified damage fracture model to predict the failure behavior for our battery under both cases or both mechanisms. And if we just zoom into the axisymmetric loading condition, we see hoop cracks. They're the damage contributors, and they're the dominant failure model for the small punch indentation. And when we just go to the large punch indentation, actually the through thickness shear fractures are the main failure mechanism again. With that, I would like to thank you for your attention and looking forward to all of your questions.